Alright, so we've been talking about the integral a whole lot and different applications of the integral, and we've talked about the integral being the area under the curve, and obviously, well, maybe not obviously, but it follows that then we can use it not only for under the curve, but in between curves. Okay, so for this problem, they ask us to find the area between the two curves, f of x, x cubed minus 2x squared plus 10, and g of x, 3x squared plus 4x minus 10. Okay, as a quick pre-calc review, which one's which? Cubic is the blue one, right? It's got two bumps, and so that's going to be the cubic, where the x squared, that's the parabola. Okay, so I'm going to label that. So g of x is the red, and f of x is the blue. Okay, so when we find the area in between curves, I'll explain a lot of the details on why this is, but what we want to do is always the top curve minus the bottom. Alright, so top minus the bottom. Okay, so what I mean when I say that is we're going to be drawing a bunch of these rectangles, alright, that are super thin. Alright, their thickness, as a matter of fact, is measured along the x-axis. We're going to call that dx. Okay, so we're going to draw a bunch of these rectangles. As a matter of fact, we're not going to draw all of them, but we're going to consider an infinite amount of them. Okay, so we know the width of each of them. The width of each of them is dx. What we need to know is the height of each of them. Okay, and so obviously, hopefully you're seeing that we want to take the y-coordinate here and the y-coordinate here, and we want to subtract those, right? You know, let's say, let's estimate this is 8, and let's estimate this is 2. So the height of this rectangle is 6. Okay, so notice what we're doing is we're subtracting the y-coordinates, right? But we want to do that in the general case. So we're going to subtract the y-coordinates. The y-coordinates are f of x and g of x. Okay, so that's the general case. Okay, so that's why we do top minus bottom. We're doing the top y-coordinate minus the bottom y-coordinate. Okay, so what we're going to do is we're going to take the integral of this, going f of x, the top curve. You notice the blue one everywhere in this area that we're talking about. Everywhere in this area, the blue curve is on top, right? So f of x minus g of x, and we're going to integrate that over x. You know, the width of each rectangle is x. And then we have to come up with some of the limits to integration. So since we're integrating with respect to x, we want to know the x values for where these intersections happen. Okay, it looks like they're -2 and 2. We don't want to assume that, but I'll show you how we can figure that out for sure in a second. We're going to go through this problem on our calculator. Okay, but I wanted to make sure we understood the logic here, that we are taking the y-coordinate on top minus the y-coordinate on bottom. How about when the y-coordinate's negative? Does that matter? Can we still do top minus bottom? Well, let's think about it. Maybe the y-coordinate there is 5, and maybe the y-coordinate here is -10. So can we still do top 5 minus bottom -10? Sorry, -10. Let's see, that gives us 15, right? Is this rectangle 15 units high? Sure is. 5 here and then 10 more here. Okay, so top minus bottom works all the time. You don't have to worry about whether or not both numbers are positive, whether or not one is positive, one is negative, or even if one is negative and the other one is also negative. Top minus bottom always works. Okay, so this is the integral in which we want to solve. If we do that, we're adding up all the rectangles like this. Okay, we're summing up all of these rectangles, and when we sum up all those rectangles, if we draw an infinite amount of them, that'll give us the exact area of this region in between the two curves. Alright, so let's go to the calculator. Okay, so I've put in the two equations, f of x, the top curve on top, and g of x, the bottom curve on bottom. Okay, and you can see my graph's going to look like that, but to get it that way, I had to play with my window first. Okay, so my x-min was -3, my x-max was 3. Remember we thought that the intersection points here and here were 2 and -2, and so I did -3 and 3 just to give us a little bit more. And then I played around with the y-scale enough just to make sure that I can see the whole shaded region. Okay, and so my graph is going to look like this, which is pretty good. And remember in the last slide, we assumed that the x-coordinate here was -2 and the x-coordinate here was 2. I want to do a quick reminder of how we did that, or how you could know that for sure. So what we want to do is we want to use the intersection feature on our calculator. So we go second, trace, which takes us to the calc menu, and then we want this option 5, intersect. Okay, then our calculator will prompt us for the first curve. We make sure we're on one of the curves. Doesn't matter which one. We hit enter. And then we got to make sure we switch to the other curve. Hit enter. And then it says guess. So we move really close to the intersection point. I'm going to find this one over here. So I'm going to move close to the intersection point. And then I hit enter. And sure enough, our assumption was good. We never want to assume that it's exactly 2, because it might be 2.1 or 2.3 or 2.12 or whatever it might be. So we want to use our calculator to double check for sure. Okay, and then we could go through the time to figure out this one, but this one's also -2. I think the coordinates are -2, -6. Okay, so what that means is that the integral that we set up before, let me flip back to it. So the integral we set up right here is the correct integral that we want to solve. That'll give us the area in between these two curves. Okay, let's go back to our calculator, but remember what we're doing here. We're doing the top curve minus the bottom curve. Alright, so I'm going to go back to my calculator now. Okay, so here I'm going to evaluate the integral using my calculator, and you can see I've already done the work, but I want to make sure we know where all these are. Okay, so to evaluate a numeric integral on your calculator, you want to go to the math menu, and it's option number 9. So if you scroll down to option number 9, that's where the numeric integral is. Okay, let me get out of here. Alright, y1 and y2. I didn't have to type in y1 and y2. Remember, y1 is our f of x, if you can read that, and our y2 is our g of x. So I was kind of taking a shortcut. You could have typed in the actual functions, you know, with the x's. That would have worked out. But I was being a little bit lazy. Since we already typed in the functions, I was using y1 and y2. Let me show you those at vars, variables. Then we toggle over to y-vars, and we want the function variables, and here's where they are. Okay, so let me get out of here. And then let's remember the calculator notation that we need to use. So what we want to take the integral of, so here's our f of x minus g of x. Then we have to say what we want to integrate with respect to, x, separated by commas. Then our lower limit, -2, and then our upper limit, 53 is 2, which gives us an area of 53.3 units squared. Okay, so that value is the value of the area in between the two curves. Okay, and in case you were curious, I worked out, instead of doing it on your calculator, I also did it by hand, but I'm not going to go through all the steps. I'll just show you the work. So if you want to see that, pause in the next few seconds. I know this is a little bit hard to see, so you'll probably have to maximize your screen and pause here, but if you want to check the work that I did analytically instead of on the calculator, you can see that we do get the same answer. Okay, so as always, if you have any questions, please write them down. Bring them to class. See y'all.